Thermodynamics. It's a word that might sound intimidating, conjuring up images of complex equations and laboratory experiments. You might think of scientists in white lab coats, surrounded by beakers and test tubes, scribbling down complex formulas on chalkboards. But in reality, thermodynamics is all around us. It's not just confined to the realms of academia or high-tech research facilities. It's in the warmth of the sun on your skin, the steam rising from your morning coffee, and even in the way your refrigerator keeps your food cold. It governs everything from the engines in our cars to the weather patterns in our atmosphere. When you drive to work, the principles of thermodynamics are at play, converting fuel into the energy that propels your vehicle. Similarly, the weather forecasts we rely on are based on the thermodynamic behavior of air masses and moisture. It's the science of how energy behaves, transforming and transferring in a cosmic dance that dictates the very fabric of our universe. From the nuclear reactions powering the stars to the metabolic processes in our own bodies, thermodynamics is the silent choreographer of this grand ballet. At its core, thermodynamics seeks to understand how energy interacts with matter. This interaction is fundamental to everything we observe in the natural world, whether it's the melting of ice, the boiling of water, or the combustion of fuel. These processes are all governed by the laws of thermodynamics. It provides a framework for understanding how heat flows, how work is done, and how systems evolve over time. Think about a steam engine, where heat is converted into mechanical work, or the way our bodies convert food into energy. These are practical applications of thermodynamic principles. It's a field of study that touches every aspect of our lives, whether we realize it or not. From the efficiency of our household appliances to the way we generate and consume energy, thermodynamics plays a crucial role. Even the simple act of cooking a meal involves thermodynamic principles. The beauty of thermodynamics lies in its elegance and universality. Its principles are not confined to a single domain but are applicable across a wide range of phenomena. This universality is what makes thermodynamics so powerful and far-reaching. Its laws, derived from centuries of scientific inquiry, hold true from the smallest atom to the largest galaxy. These laws are the result of meticulous observation, experimentation, and theoretical development, standing the test of time and scrutiny. Understanding these laws unlocks a deeper appreciation for the intricate workings of our world and the cosmos beyond. So, buckle up. As we delve into the principles of thermodynamics, we'll uncover the hidden mechanisms that drive everything from the simplest chemical reactions to the most complex astrophysical phenomena. We're about to embark on a journey into the fascinating world of thermodynamics. This journey will take us through the fundamental concepts, the groundbreaking experiments, and the real-world applications that make thermodynamics an essential part of our understanding of the universe. Prepare to have your mind stretched, your curiosity piqued, and your understanding of the universe we inhabit forever changed. As we explore the depths of thermodynamics, we'll see how this field of study not only explains the world around us, but also inspires new ways of thinking and innovation. Before we dive into the laws of thermodynamics, let's establish some ground rules. Understanding the basic concepts of systems and surroundings is essential for grasping the more complex principles that follow. In thermodynamics, we talk about systems and surroundings. These terms help us define the scope of our study and focus our analysis on specific areas of interest. Think of a system as our object of interest, like a pot of boiling water on a stove. This pot of boiling water is our system, and it is where we will focus our attention. Everything else, the stove, the air, the kitchen, becomes the surroundings. The surroundings include everything outside the system that can interact with it in some way. Systems can be open, closed, or isolated, depending on how they interact with their surroundings. These classifications help us understand the different ways energy and matter can be transferred. An open system exchanges both energy and matter with its surroundings. Think of that pot of water, releasing steam and heat. In this case, the pot of boiling water is losing water vapor to the air and gaining heat from the stove. A closed system, like a sealed thermos, can exchange energy, heat, but not matter. The thermos can gain or lose heat, but the liquid inside remains contained. An isolated system, though difficult to achieve perfectly in reality, exchanges neither energy nor matter with its surroundings. This is an idealized concept, often used for theoretical purposes. These distinctions are crucial because they help us define the boundaries of our analysis. By clearly identifying what constitutes the system and what constitutes the surroundings, we can better understand the interactions and energy exchanges that occur. By focusing on specific systems and their interactions, we can begin to unravel the complexities of energy transfer and transformation. This understanding is fundamental to the study of thermodynamics and helps us apply these principles to real-world scenarios, from industrial processes to everyday phenomena. Energy transfer can occur in various forms, such as conduction, convection, and radiation. Each type of energy transfer has its own unique characteristics and plays a vital role in how systems interact with their surroundings. Conduction involves the transfer of heat through direct contact. For instance, when you heat one end of a metal rod, the heat travels along the rod to the cooler end. Convection, on the other hand, involves the movement of fluid, such as water or air, transferring heat as it moves. Boiling water creates convection currents that distribute heat throughout the pot. Radiation is the transfer of energy through electromagnetic waves. The sun heating the earth is a prime example of energy transfer through radiation. By understanding these different types of energy transfer, we can better analyze and predict the behavior of systems in various conditions. This knowledge is not only crucial for scientific research, but also for practical applications in engineering, environmental science, and many other fields. As we continue to explore the laws of thermodynamics, keep these foundational concepts in mind. They will serve as the building blocks for more advanced topics and help you appreciate the intricate dance of energy and matter in our universe. The first law of thermodynamics is often paraphrased as energy cannot be created or destroyed, only transferred or transformed. This means that the total amount of energy in a closed system remains constant over time, even though it may change forms. It's a fundamental principle that governs all energy transactions in the universe. From the smallest atom to the largest galaxy, every process is bound by this law. Imagine you have a battery. This small, seemingly simple object is a powerhouse of stored energy. It contains a certain amount of chemical energy stored within its materials. This energy is waiting to be released and transformed. When you connect it to a light bulb, that chemical energy is converted into electrical energy, which then transforms into light and heat. The light bulb glows, illuminating the room, and you can feel the warmth it emits. The total amount of energy in the system, battery, wires, bulb, surroundings, remains constant, even though the energy has changed forms and location. This is a perfect demonstration of the conservation of energy. This principle has profound implications. It dictates how we understand energy use and efficiency in everything from simple machines to complex ecosystems. It means that there is no such thing as a perpetual motion machine, a device that can produce work indefinitely without an external energy source. Such a machine would violate the first law of thermodynamics. Every action, every transformation, every process in the universe requires an energy input. Whether it's a plant photosynthesizing sunlight, a car burning fuel, or a star shining in the night sky, energy is always being transferred and transformed. There's no free lunch in the cosmic diner. This means that to get something, you always have to give something in return. Energy must come from somewhere, and it must go somewhere. This balance is what keeps the universe in motion and in harmony. Throughout history, humans have harnessed this principle to develop technologies that transform energy in useful ways. From the steam engines of the Industrial Revolution to the solar panels of today, our progress is built on understanding and applying the first law of thermodynamics. Looking to the future, this principle will continue to guide us as we seek sustainable energy solutions. By respecting the law of energy conservation, we can innovate and create technologies that are efficient and environmentally friendly. So remember, you can't get something for nothing. The first law of thermodynamics is a reminder of the balance and interconnectedness of all things. It teaches us that energy is precious and must be managed wisely. Section 4. The second law, entropy, the universe's tendency towards disorder. The second law of thermodynamics introduces the concept of entropy, often described as a measure of disorder or randomness. It states that the total entropy of an isolated system can only increase over time. Think of a pristine, organized room. Left to its own devices, it will gradually become messier. Books will be misplaced, clothes will pile up, dust will settle. This natural tendency towards disorder is what entropy embodies. In the grand scheme of the universe, the second law implies that the total amount of disorder is always increasing. Stars burn out, heat dissipates, and systems move towards a state of equilibrium where energy is evenly distributed and less available to do useful work. Section 5. The third law, reaching absolute zero, a cosmic impossibility. The third law of thermodynamics deals with the concept of absolute zero, the lowest possible temperature that can be achieved, theoretically, which is minus 273.15 degrees Celsius or 0 Kelvin. It states that the entropy of a perfect crystal at absolute zero is zero. This law has profound implications for the nature of matter and energy. As a system approaches absolute zero, its entropy approaches a minimum value, and its molecular motion slows to a near standstill. However, the third law also implies that reaching absolute zero is impossible. While scientists have come incredibly close to reaching absolute zero, achieving it would require a complete cessation of molecular motion, a state that seems to be unattainable according to our current understanding of physics. Section 6. The zeroth law, establishing thermal equilibrium. The zeroth law of thermodynamics might seem a bit out of place, but it's a fundamental principle that underpins our understanding of temperature and heat flow. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Imagine you have 2 cups of coffee, one hot and one cold, and a thermometer. If the thermometer reads the same temperature when placed in each cup of coffee, we can conclude that the 2 cups of coffee are in thermal equilibrium with each other, even if they have different amounts of thermal energy. This seemingly obvious law is crucial because it allows us to define temperature as a measurable property, and to understand how heat flows between objects at different temperatures. If you found this video helpful, please like, share, and subscribe for more detailed overviews on fascinating topics like thermodynamics.